Hello, this video is entitled Stokes Theorem. Now with Stokes Theorem, we're essentially looking at a higher dimensional version of Green's Theorem. So in Green's Theorem, you may recall, we related a line integral to a double integral over some region. In this section, we're going to relate a line integral to a surface integral. So let's look at the surface with indicated orientation here. And you see you have all these normal vectors sticking out at different points. So we're going to be using surface integrals. Let's come down here. I'll let you kind of look this over here. So what is this saying here? Think of the positive orientation of C. Think of yourself walking along the curve. While you're walking along the curve, if your head is pointing in the same direction as the unit normal vectors, while the surface is on the left, then you are walking in the positive direction on C. Well, I wouldn't worry about that too much. Once again, I'm sticking with the idea of upwards, so we're doing... Alright, so S is an oriented surface with a unit normal vector n, bounded by a piecewise closed curve C in a positive orientation. If F is a vector field whose component functions have continuous first partial derivatives on the functions S and C, then F dot dr, the line integral, can be evaluated this way. The curl of F dotted with n, which n is going to be the same thing it was in the surface integral section. Change that to same color I had in the other video. Not that it matters, but so it's going to be the same vector, negative zx, negative zy, 1, and then we'll have to get the curl. Remember, the curl was that vector we have a formula for. Okay. And they're telling us the theorem the surface S can be any surface as long as its boundary curve is given by C. That's something that can be used to our advantage to simplify the surface integral on occasion. All right. Don't know if we're going to need to do that or not. But evidently there could be some situations where it would simplify something that's more complicated. We should be able to use this theorem pretty much just straight up as is. So use Stokes Theorem to calculate the curl dot n ds. And here's the vector field for m, n, and p. And here's our region. 7x plus 8y plus 3z equals 5. First quadrant makes everything positive. Here's our formula. There's our curl formula we haven't seen in a while. So we just follow that. Partial of p respect to y, no y, that's 0. N with respect to z, no z, 0. Middle one, m respect to z, 0. P with respect to x will be 0. Finally, we'll get some numbers here. N, the middle one with respect to x will be 5. And then m with respect to y would be negative 3. So it's 5 minus a minus 3. So the curl is the vector 0, 0, 8. Now to do this, we're back to double integrals now, not triple integrals like for the divergence theorem, Gauss theorem, same thing. So that means our z's have to be converted into y's and x's. So we take our plane equation here, solve for z 1/3, 5 minus 7x minus 8y. Now I could distribute that out, but as long as you remember when you're taking the partial derivatives, just make sure the 1/3's in there. So the zx would be the derivative of this negative 7 times that 1/3, so it's negative 7/3. And then the zy would be negative 8/3, because it would be negative 8 times that 1/3. So then remember the normal vector is the negative of zx, negative zy. So they're both negative. That changes them to positive, and then 1 is the constant third one. So now we have to do a dot product. Well, that's going to be super duper easy. 0, 0, 8, dotted with 7/3, 8/3, 1 will just be 8. So curl dot fn, in this case, just equals 8. But then now we have to get our limits of integration. Now there'll be no need for this one to be polar. You know, this will be just x and y. So we go up here. And in the xy plane, we know that z equals 0. So from this equation, we can just zero out the z right here. And you're left with 7x plus 8y equals 5. Now, it doesn't matter, you know, if you want to solve for x in terms of y here, that just means you're going to go dx, dy. I'm just going y in terms of x, so therefore my order of integration will be dy, dx. So just kind of move this around, solved it, got 1/8 times 5 minus 7x. So that's for the dy. Then for the x, that means we zero out the z, which we already done. We also zero out the y, because remember the outside limits of integration are x. So, or constant, I mean, constant in terms of x in this case. So 7x equals 5. So x equals 5 over 7. So it goes from 0 to 5 over 7. So antiderivative of 8 dy would be 8y. We plug in this upper limit. The 8 kills the 1/8, so that goes away. So essentially 5 minus 7x goes in for the y. 0 to 5 over 7. Integrate this. Be 5x minus 7/2 x squared. Put in 5, 7 minus 0. Obviously use a calculator to do that, but anyway, it's fine. And I got 25 over 14. Oh, be careful, there's a negative 25 over 14 there. But there it is, which I think it could be negative. So it doesn't eliminate the negative. I was just making a note that's kind of close there. All right, let's see what's next here. Here's another Stokes theorem. This one's kind of unique. So here's the vector field. We've got I don't like the way that looks there. That should be, I didn't type this, but that should say XY plane, XY. It should have the Y in front. It should look like this. You can see planes on the next line. I'll just do it right here since I'm not going to fix it officially. You know, it should look like this. It should say X. I guess I didn't notice that before. And then the word plane right there. XY plane. Not X minus Y. Bounded by the x-axis, y-axis, z-axis, let's see. And the line y equals 3 minus 4x. Now this is a little bit different than the last one, a little trickier here, just because, you know, normally this equation right here has x, y, and z, where we're solving for x, z in terms of y and x, you know, and then we're taking the zx partial and the zy partial. But all we need is a normal vector coming out of this thing. So think of this region. And this will be a terrible looking sketch here, unless I pause and try to bring up a nice looking 3D coordinate system somewhere, but all right, this is going to be not so good here. So for y equals 3 minus 4x, the intercepts are going to be, when x is 0, y would be 3. And then when y is 0, x would be 3/4. So it's going to look something like this. There's your line. Well, anyway, so you're in the xy plane. So obviously when you have all three variables, it's some other plane somewhere, and you're getting a normal vector. But this one, since it's on the xy plane, I'm putting a hint right in here that anything that sticks straight up vertically qualifies as your normal vector. I said k, but obviously I could have said 2k, negative, remember k is 0, 0, 1. But obviously anything would have worked here. 0, 0, 2, 0, 0, negative 1. But anything going up and down vertical on the z-axis would be the normal vector here. But a little bit weird without that z, I have to admit. A little different than the way we did it before. But now we've seen how to handle this. I just showed the numbers for the curl. I didn't even bring the formula down here, but you end up with a, I guess, I don't think this is always true, but it sure seems this way for the ones we've been doing here, but I don't think it's a rule. But these all zeroed out, and we just ended up with 0, 0, 3 performing that curl. You know, I have the curl formula on the previous page if you want to work that out just for practice. So curl.n will be 0, 0, 3 dotted with what I was explaining right here about the k, 0, 0, 1, which gives me a 3. So we're going to integrate 3 dy dx. Now I just kind of drew a little triangle right here. I chose dy dx, so I want y 3 minus from 0 to 3 minus 4x going vertically, and then x would go from 0 to 3/4. You might not like that 3/4, so you might want to go dx dy. But there's really no need to. All right, so this isn't too bad. Antiderivative of dy would be y, so I'll put in the 3 minus 4x. And now I'll plug in the 3/4 and the 0, so you're going to get... I'm sorry, no. That's the next step. I integrate this, then I'll plug it in, excuse me. So the antiderivative of 3 is 3x. Antiderivative of 4x is 2x squared, so it's 3x minus 2x squared with that 3 that's been sitting there from here. I pulled it to the outside. Now I put in the 3/4 and the 0. So you put in the 3/4 here. The 0, of course, will be 0. You know, obviously use your calculator for that. It ends up being 27/8. There it is. Kind of sneaky. See how those two negative, and the negative and the positive? Yeah, you might want to think, hey, it's got to be one of those two. You know, also obviously that was true in the last example, but not here. So don't try to outsmart the answer choices too much there. Just work it out, and it should work out just fine if you do everything properly. Oh, let's see what I did here. I think I did some unnecessary stuff here just to expand our learning. I parameterized it. Remember I did that. If you watched that one video that I did that on Green's theorem. And I also did it on the conservative vector fields and independence of path. I think I did it there. But I know I did it in Green's theorem. So anyway, don't worry about this at all. But I came up with the 3 paths according to this. And I did f dot dr. Well, actually, setting this up would be the hard part. But actually, f dot dr ends up being 0 for this one, C1 and C3. I guess I didn't show the work there, but I guess I probably just saw, because you go back up here and you substitute. Let me at least try to explain that. So we're substituting into this equation. All right. I'll put it right here. Well, C1 is going to have a dr of 3/4 0, 0 when you take its derivative. So when you put this, y is 0 right there. So right there when you substitute, you have something that's 0 right here. This won't be 0. It'll be 9 times 3/4 t. And then this one will be 0. So you've got 0 something 0 dotted with something 0, 0. So you're going to have a 0 involved in each of the multiplications. So therefore you're going to get 0 for that one. And sort of the same logic for C3. you're going to get, see this, you plug the y in right there, so you're going to have something here. You plug in x, you get 0. And you plug in the z, you get 0. So when you dot it with the derivative of this, which is 0, negative 1, 0, you're going to get 0 there also. So, so that one ends up working out where you only needed to do C2. But anyway, I did C2, f dot dr, and I got 27 over 8, which was the same answer we got using Stokes theorem. So just wanted to show you that, you know, we've seen Green's theorem to evaluate a line integral, and now we're using Stokes theorem. So let's see what's happening here. Here's our vector field. Hemisphere. Okay, hemisphere tells me we might be looking at sphericals here. Coordinates. I mean polar, because this is not a triple integral, excuse me. Even though it's, yeah, even though it looks, it's not a triple integral, so it would not be spherical. Alrighty, I did not show the steps for the curl other than just the numbers. Why, this is weird. It ends up 0, 0 something. I don't want to say that that's a 100% rule there, but it's certainly for these examples it turned out that way. Obviously you could probably make up something that didn't do that, but it's weird. So it ends up being 0, 0, 2. Now I'm getting the, because I'm doing this thing again. The negative zx, negative zy, and 1. So I have to solve for z in terms of x and y, upper hemisphere, so it's just the positive square root. And we've seen this kind of idea before. So you take each of these derivatives, and the 2's cancel, of course, and the derivatives of the inside. Yeah, we saw one very similar to this before. Not in this section, but might have been on either surface integrals or the Gauss theorem, divergence theorem. I don't remember. Probably surface integrals, because that's a double integral. So there it is. So and remember, all these there's negatives here, but remember there's negatives in this normal vector. So the two negatives here cancel the negatives that were there, so that's why they're both positive. But you know what? No matter how bad, I guess actually, you know, if you hear something, there's a little shortcut for you. And this obviously works for this, but it's not a rule you can use every time. Yeah, you know, actually, since these are 0, 0, it really isn't even necessary to compute these, because when you dot product them, they're both going to be 0 anyway, right? So really the dot product ends up just being 2 times 1 is 2. And so you're just integrating 2 across the area region. So in the xy plane, so essentially you're taking that hemisphere and you're mapping it down to the xy plane. What would it look like just on the xy surface? And means just 0 out the z. So on the base, then, it's just a circular base. X squared plus y squared equals 81. Definitely polar. So we're at the 2, we're integrating 2. Now it'll be r dr d theta. We go from 0 to 9, 0 to 2 pi. Antiderivative of r be 1/2 r squared. 2's cancel. 9 and 0 make 81. And then we're integrating d theta for the last one, so that just brings in a 2 pi. So it's 81 times 2 pi, which is 162 pi. And there we are. (162 pi). Here's something that I just sort of copied out of a book there. I don't know if that really, you don't have to worry about any of that or whatever, but I just saw this, I thought I'd copy it, and measures the circulation of F around C. Okay. Oh, this is a little bit better though. Physical interpretation of the curl. The curl is a vector field that measures the tendency of the vector to swirl around. So it says, imagine that the vector field represents velocity vectors of water in a lake. If the vector field swirls around, then when we stick a paddle wheel in the water, it will tend to spin. All right. So I guess like no curl, no spin. And down here, I'm just including, which obviously is not necessary. I made that normal vector be sort of gigantic looking there, but anyway. Well, actually, that arrow is the curl. And here's the vector field. So you see it's kind of swirling around there, and the curl is being measured as that upward vector. Remember, curl is a vector, so that would be it. Sticking up, and there they are, kind of rotating around there. All right. Not critical for you to know that. Maple graph below represents a vector field for a problem back in 15.1 where the curl vector was, that section 15.1 is entitled Vector Fields. I want to clear that up just in case. I'm trying to eliminate the section titles from the videos because to allow for different books in the future. But right now, I'll just put that in there so that way there won't be any confusion if it's actually a different number section from a different textbook. So 0, 0, 0. So yeah. So notice that this is not swirling in a swirling motion at all. No curl. No curl vector to be seen. 0, 0, 0. Not swirling all over the place. So that's why no curl. All right, let's look at another example. I believe this will be the last one. Yeah. All right, so here's our vector field, and there's our surface, z equals x squared, from 0 to 3 for x, 0 to 3 for y. There's the curl formula. Okay, this one, I must have went looking for another problem because I'm glad too. I'm glad we're doing this one because I was getting frustrated with all the curls being, 0, 0, some number, because I did not want to indicate that that was always going to be the case. So thank goodness we have one here that is not that way. All right, so just follow the curl formula, and this time you're going to get 0, xy, negative xz. Now we're going to take z equals x squared, and we're going to find the x partial and the y partial of this. So the x partial would be 2x, and the y partial would be 0, because there's no y. So there's zx and zy, and remember the normal vector is negative zx, negative zy, 1. So that turns that to negative 2x. Of course, 0 still remains 0, and that was always going to be a 1 there at the end. So we have to dot these two. But the z needs to not be there, because this needs to only be x's and y's because it's a double integral. Well, no problem. We know that z equals x squared. So these two actually dot out to be 0 just because of the order of the zeros, correct? 0 here, 0 here. So now I'm going to take this information that we already have, that z, I might have said x cubed. If I did, that's wrong. Z equals x squared, and you plug that in there, so that's going to make this term negative x cubed. And then when you dot product, you multiply that by 1. So I just wrote there's what it is right there, negative xz. You could either do it like I was about to do, or you can wait till afterwards and do it right here. That's maybe, yeah. Then now you change it. Either way, you end up with negative x cubed because we do not want that z. And this was a rectangular region, I assume. Double check that. Oh, yep, that makes it nice and easy. So we go 0 to 3, 0 to 3, negative x cubed dy dx. So it's negative x cubed y, which is 3 and 0, puts a 3 in there. So it's negative 3x cubed dx. Antiderivative of that would be negative 3x to the 4th over 4. Put in 3, put in 0, and you get negative 243 over 4. Let me double check that. Ta-da! There it is. And that concludes this video on the Stokes Theorem.